Okay, so the last thing I want to talk about is, can you get gain using just resistors, capacitors, and inductors? You can't get power gain or energy gain because that would violate the first law of thermodynamics and energy conservation. But you can get voltage gain. You can produce voltages that are higher, say, than your input voltage. And here's how you do it. We look at this as a voltage divider network, that this impedance is on the bottom, this impedance is on the top. V out then would be an expression V out over V in equals this equivalent Z here, which is the parallel combination of the inductor and the resistor, divided by Z plus the impedance of the capacitor. Same formula as voltage dividers. If you had R1 on top and R2 on the bottom, this would be R2, R1 plus R2. Okay, so far so good. And then you work through the equations and you get this. I sometimes like to make sure that they're saying the right things. So we can work out the Z, J omega L, and times R divided by the sum of J omega L plus R. All of that divided by, and I want to, there we go. There we go, equals. There we go. Or should I put the equal sign down here? V naught over V in down here to make it clearer. There we go. Okay. Bottom part, J omega L R over J omega L R plus R, J omega plus R. And then gotta erase this part. There we go. So that Z plus 1 over J omega C. I'm going to multiply top and bottom to get this result here. I have to multiply by J omega L plus R over R. So that'll make this equal to, well, this will cancel this, and this will cancel this. So we get the J omega L on top. And then this times this will give us just J omega L again. J omega L again. That's this stuff here times this stuff. You'll have L over C as a real number. When you multiply this times 1 over J omega C, you'll get an L over C and an L over CR. Okay? And then finally, j omega, yeah, this times this, the first term, j omega L over R times 1 over j omega C, L over CR. R, well, anyway, the last one, you just have 1. 1 times 1 over j omega C. Rearranging this a little bit, now we can see how we derive this equation. One over j is negative j. So we're going to get j omega L minus 1 over omega C plus L over CR. The real part, the imaginary part. Okay. Now, you want this to be 0. Okay, let's. So now we can see that equation. I can erase all my ink and see what the book says. Okay, so no, I'm sorry. That you want this term to be 0, not too far off. This term to be 0. You're going to get this gain. And you choose the capacitor to make that happen. And then once you have the capacitor, let's see, we have the kilohertz, R equals 100 ohms. Once you know the frequency, capacitance, then you can get the this has to equal 10, V over out over V in equals 10. We know R, we know omega. We can find C. Once we get C and we know omega, we can get L. There we go. So you'll get voltage gain, not energy gain. That's important to note. Okay. Now, here's something also, that this is a way to prevent DC biases. Low impedance at 1 gigahertz, DC bias, and block DC. So all we have coming out is an AC signal. The solution to that, well, a capacitor blocks the AC. Infinite inductance would be an open circuit. Or I'm sorry, j omega L. Yeah, infinite inductance would be essentially Z equals infinity. And so you would have a bias. This right here will put a bias on it. You have an open circuit here. You wouldn't have any DC voltage, any kind of DC circuit here. The DC voltage would be determined by this right here. And then you have an AC signal too. So you can't make L infinite, but you can make it reasonable. This is impedances which have a ratio of 10,000 to 1. So picking picking out a couple values, you can come up with a reasonable number. So you get a V out, which is you're summing. Let's see, where's V in? Blocks DC. V in would be like a DC signal, a very low frequency signal. This would be the input signal, and this would be the output signal. So we can get something really close. Let's see. Anything else I need to say? Oh, yeah, one more thing. XC. This is called reactance. It is the impedance of a capacitor without the J. This is the impedance of the inductor without the J. That's one thing they didn't talk about in the other slides. You see that JXL gives you the impedance of the inductor. Take that. Yeah, XC equals 1 over omega C. So you're missing the 1 over J. You're missing the imaginary parts here. That's called reactance. End of slides, finally, at this chapter. So let's quit it and